I'm Jun Yang, a postdoc from MIT Kavli Institute. I'm here to talk about measuring silicon X-ray absorption towards bright sources in the galactic bulge, including how to measure the silicon gas to dust ratio with the Chandra high energy transmission gravity spectrometer. Knowing the dust content with silicon in interstellar matter is necessary to understand the heating and cooling process in the interstellar medium, which dominates the star formation rate in our galaxy. We use Chandra HETG data to measure the broadband hydrogen column density in these bright, low-mass X-ray batteries. The goal is to obtain silicon gas to dust optical depth ratio towards different line of sight in the galactic bulge. These are the elements that absorb X-rays. This shows the cross-section for hydrogen nucleus from the Gardner dust model based on Christine Oliver. We specifically focus on the silicon Kedge. Besides the absorption, we can say the scattering significantly contributes to the extinction. We use the new Chandra data. We are well calibrated with a pair of 3, specifically measure the silicon Kedge. We have enough exposure time for each source. This map shows the location of this source. The background is the Wisconsin H-alpha mapper survey, and the source labeled in black are part of our current survey. First, we have got the broadband hydrogen column density comparison with the other mission. We can say the H value from Chandra are higher than the value from the other instrument because Chandra exclude the scattering and the other missions regain the scattering. So the H value from the other instruments are systematically lower than the Chandra because they are model dependent. With a larger H value, they are more likely diverge and more scattering goes away because they all are below the equality line. And we also put the silicon broadband silicon abundance as a function of the H value. They are all above the unity line. This indicates the different silicon moleculars or atomics because they are highly silicon abundant. And this figure shows the silicon optical depth comparison between different instruments. On the left is the gas edge optical depth as a function of the H value. They don't comply with the William Allen McRae prediction because their model didn't consider the dust. On the right, the gas versus the gas plus dust optical depth for every source. The scattering indicates these sources are model dependent. We also sum with a pair up. And therefore, we can only say the very high resolution structure of the silicon Kedge with the Chandra HETG observation with the highest resolution. This is an example for GX2 plus 1. This is atomic silicon Kedge. This is silicate Kedge. Here we show 2 extreme cases of the high resolution structure for silicon edges. On the left is for GX2 plus 1. This is shows a significant gas and dust optical depth. On right is a GX5 minus 1. It is dominated by the dust. Only weak gas edge optical depth contributes to the structure. We have put the gas and gas plus dust optical depth ratio in this figure. On the left is all data the scattering due to different instrument mode. On the right we can say most of them are consistent with the MRN standard dust distribution. There are only some exceptions. For example, GX-1, the dust plus gas optical depth ratio optical depth is 6 times of its gas optical depth. So finally, we have obtained the gas to dust optical depth ratio for X resources in the Galactic Bulge. These ratios are data relevant and completely independent of any edge modeling. This data show varieties from very dusty edges, as for GX5-1, to some sources with only little dust contribution, for example, GX3+1. Now we are focusing on using the syndicate models to determine the mass column densities, abundance, and possibly modified cross-section. The next step, we will include the analyze the syndicate models in our final phase. Thank you. I would like to take the questions.
Well, thank you. You've finished ahead of time. You actually give us 20 extra seconds and a minute for your questions. Do we see questions coming up somewhere on the chat? Being able to tell the difference between gas and dust is really a powerful thing, but of course you need an X-ray continuum in order to do that. You're doing this against X-ray sources, so there has to be a continuum to provide the continuous background to see the absorption edges.
Yes, that's right.
Love to be able to do that for stars, but we don't have enough X-ray background. Are there questions? Let's see, chat. Oops, that's your timer. Randall wants to know, are you building your own models to test the newest calculated opacities?
We are using now we are using the Zagos model to determine syndicate moleculars, and next we will use the analyze syndicate models to interpret the structure.
Okay. Someone asked, Javier Garcia wants to know, said it's a great talk. Can you say something about the current contamination of silicon in the Chandra detectors?
So current, you mean the contamination is other contamination from the other source, or the modes of the detector? So I'm not sure if I answered the question correctly. That from the previous data, we didn't exclude the consider pair up factor. So now we use new. So the new data, they are pair up free, and the edge was resolved.